So today's lesson is all about logarithms. Now, what is a logarithm? A logarithm is an inverse of an exponential. So just like we did inverse of a quadratic was a square root, the inverse of an exponential is a logarithmic function. And we're actually going to practice graphing both of them on the back. But today we're really just going to look at writing them, evaluating them, and also graphing them. We'll do that with a calculator and without. So the warm-up just asks us to solve each equation using inverse operations, or you can also think like, what number can I plug in for x that would get me 8, for example, or what number can I plug in for x that would get me 27. So what do we think for number 1? 8 equals x to the 3rd. Awesome. 2, positive 2. How about the next one? Jade?
Is it 16?
Yes, it'll be 16. 2 ways you can do it. You can use inverse operations, which remember when you have these rational exponents, you would raise it to the reciprocal power, which would be the 4th power. And then 2 to the 4th is 16. Or you can also think that the 1/4 power is the 4th root. So the 4th root of what number gets me back to 2, and that'll be 16 as well. So however you think of that. Now this one, you can't take the x root of a number. You have to actually think like, what would I plug in to get 27? So what would we get for x there? 3 to the what power gets me 27? Abby? 3. And then this one, 4 to the 6 will equal 4 to the 3x. So what number would need to go in for x so that it would be 6? Okay? Nope. Sam? 2. These are being multiplied. So if you put 3 in there, 3 times 3 would get us 9. So it would have to be 2. All right, so a logarithm, again, is the inverse of an exponential function. And so the relationship between an exponential and a logarithmic are, you'll see a lot of the same letters. You'll see an x, a y, and a b. B is considered the base, because it's being raised to a power. So we're used to saying y equals a times b to the x. Today you're just going to see y equals b to the x. There'll be no a value. Now when you talk about a logarithm, you'll notice that it has a little subscript. That's also considered the base. So you'll notice that the base of the exponential is still the base of the logarithmic. So whatever number is in for the base, it stays the base in both of them. Now, you will notice that the y and the x kind of stay on the same sides, but instead of being exponential, they're now no longer exponential. Now, one relationship, I should tell you how you read this. So whenever you look at this, you would say it's log base b of y equals x. So this will usually be a number. Log base 2 of x, or log base 10 of x. Right now they're all letters. But there is a kind of relationship between them, and that's the base is always the base. And there's a counterclockwise swoop that can help you change from logarithmic back to exponential. You want to draw this in. So this would be b, the base, raised to the other side's power will equal what you were taking the logarithm of. So this would be b to the x equals y, which is what we had over here. So anytime you're changing from logarithmic back to exponential, you'll use this counterclockwise motion to help you see what's being raised to what power. Okay, but the big key is the base stays the base, whether it's the base of the exponent or the base of the logarithm. Okay. This just talks about how negative exponents do not result in negative answers, and you'll see that in a second. So the logarithm of a negative number or 0 is undefined, so it can't be done. And you can also test that in your calculator. So we are asked to write each equation in exponential form. So we're going to write it back in something to the something power equals something. And we're going to be able to verify that these are true. So this would be read log base 5 of 125 equals 3. So again, this is the base. That'll be the base of our exponent. It'll be 5 to the something power. So again, if you're going from logarithmic to exponential, you're going to go in a counterclockwise swoop. The base of the logarithm becomes the base of the exponent. So this will become 5 to the third power, and then you bring your equal sign before you go around, and that will be equal to what you were taking the logarithm of. And we know 5 to the third does equal 125. The next one, the base was 2, so this will be 2 to the fourth is equal to 16. They're not always going to be this easy. We're going to throw in variables, and you're going to have to solve them. This is just practicing switching it all around. What would the next one be in exponential form? What to the what power equals what? Abby?
3 to the 5th power equals 2 to the 3rd.
Yep. And the last one would be 6 to the 2nd power equals 36. Next set of 4 examples ask us to go from exponential back to logarithmic. So again, remember that the base stays the base. So this will be log base 2. You will switch the numbers around though. So it's not log base 2 of 5, it's log base 2 of 32 equals 5. And you can think, because whenever we did inverse, remember we would switch the x and the y. That's kind of why the logarithms, the values will switch around. So again, identify your base first, because that's going to go in the base position, our subscript. Log base 3 of 729 equals 6. Now, you can have fractional bases and answers. So this one would be log, the base of the exponent is 1/2, so that's the base of my logarithm. So log base 1/2 of 1/8 equals 3. And you can check them by going backwards. 1/2 to the third power equals 1/8. Kind of doing that counterclockwise swoop again. And then this last one, we have our base of 10, which we'll talk about on the back, is called the common base. Log base 10 of 1 is equal to 0. 10 to the 0 equals 1. All right, now that we've practiced just converting from one form to the other, we're actually going to solve them without a calculator. To do this, you probably want to go ahead and make it into an equation and tell me that it equals a variable. I usually just use x, because it makes it a little bit easier. So, you don't know what log base 3 of 81 is, but we can change it to exponential form and then think about that number to what power would get me the other answer. So we're going to change to exponential, and then you're just going to think, what number would I plug in for x and get that answer. So remember, the base of the logarithm is the base of my exponent, and then I do my counterclockwise swoop around. So this would be 3 to the x power equals 81. And then you literally just have to think by guessing and checking what number goes in for x. So 3 to the what power gets me 81? Actually, 4. And if you had this on your no calculator part, you can just list them off to the side if you don't remember. We'll get 9 times 9, which is 81. So you'll see on my answer key, sometimes I put x equals 4. The answer is really just 4. You don't need an x. You just have 4 with a circular box around it. All right, the next one, I want to change this. Is it changed on your paper to 32? Yeah? Okay. I also changed this one. I think on your papers it's good. Just didn't do it on my board. All right, so same thing. Change this to exponential. So this would be 32 to the x power equals 1 over 32. What do you think we could fill in for x that would make 32 become a fraction? Hannah? -1. So sometimes you will see negative answers. They don't get you a negative value, they get you a fraction by moving that to the denominator. So our value of this is just -1. Now notice the next one is actually going to get smaller as well. So 9 to the x power equals 3. Anytime the value is getting smaller, that means that this exponent must be a fraction. Remember, a fraction represents a root. So an index of a root. So we know the square root of 9 is 3, so this has to be the 1/2 power. 9 to the 1/2 would be 3, so x is 1/2. And the last one's a little bit easier. 10 to the x power equals 100. That would be 10 to the second. So x is 2. All right, now we're going to look at the calculator. There are a couple buttons on our calculator for logarithms. Now your calculator will only do these two, the common logarithm and the natural logarithm. So the common logarithm is a logarithm with a base of 10. So if I were to tell you log base 10 of x, you can actually write this as just log of x. Anytime you don't see a base, the 10 is understood. Now if there is a base written, like a 2, then you know the base is 2. Or if you see a 7, the base is 7. But if there's no base, it's just understood or implied that it's 10. Kind of like when we write x, we don't always put a 1 in front of it. It's implied that there's a 1. The same thing here, you'll just imply that that's a base of 10. Now the natural logarithm is written as ln of x, but this would really be log base e of x. Now e is a number, just like pi, 3.14. Okay, if you go to your calculator, you should see the e button. I know where the e to the x button is. Where's our just e? Right here. I usually use the e to the x button, which so will you, but if you press second and the division symbol, you'll see what the value of e is. Okay. And this is called Euler's number, if you want to jot that down. And it's approximately 2.71828. It's an irrational number, just like pi, but it's used in logarithms when we're doing natural logs. Now instead of writing log base e of x, especially since e is this crazy number, this will be written as ln of x. And you'll probably see that button on your calculator if you glance around. Our log button is right here. Okay, again, your calculator automatically does log base 10 all the time. So I'm going to teach you guys a formula, maybe tomorrow, called the change of base formula, where we can actually change the base in our calculator. And then you should see right below it the ln button, which is the log base e, which is called the natural log. You'll do a lot of stuff with these two things in pre-calculus and a lot of stuff in calculus with the logarithms. For 17 through 20, all they've asked us to do is to evaluate each logarithm using your calculator and round to the nearest thousandths place. So if you're finding the log of 900, you're just going to take log, type in 900, nothing fancy, and hit enter. We'll round to the nearest thousandths place, which is 3 decimals out, so that'd be 2.954. So sometimes logarithms aren't going to get us a nice, neat answer. Natural log of e, oops, this will press the natural log button. And then again, to get e, I pressed second and divide by. See that little e up there? We should get 1. Now that one should make sense if I were to actually solve this one by hand. Remember that the base of a natural log is like an e, so this would be e to the x power equals e. So e to the what power equals itself, x would be 1, in case you wanted to do that one by hand. But natural log of a negative 1.87. How do I keep this in a second? And we should get an error. Non-real answer. So this answer would be undefined. Doesn't exist. When we look at the graph of that, we will see why. And the last one, we should have a problem. Has a log base 2. Our calculator only does a log base 10. So this is not possible to put in the calculator. At least right now, I haven't taught you the formula yet. So if it's not possible to be typed in your calculator, we'll have to do it by hand. So again, set this equal to an unknown value, x, change to exponential, so this will be 2 to the x power equals 16, and then just think, what number do we have to plug in for x? 2 to the what power gets me 16? It is 4. Okay, so just be aware the calculator only does it if it's a log base 10. All right, last problem is graphing. So I talked about this on the front when I introduced logarithmic functions. They are the inverse of an exponential function. So you can actually see that part of one has been drawn here for you. I think yours actually shows up the whole way, but we're going to practice graphing a logarithmic function. Now obviously if you wanted to graph this with your calculator, you could go to your y equals button. Oh no, we can't. This is a log base 2. Our calculator will only do log base 10. So we can't do this, the calculator in this one, but we could if it was a log base 10. So there's 2 ways that you can graph, okay? So to sketch the graph, you can either use the fact that the graphs of the 2 functions, remember that they are reflections across the line y equals x. So you can change this to exponential, graph the exponential function, and then reflect it across the line y equals x. But a lot of you, whenever we did inverses, did not like this. So many of you preferred to do a table of values and then just switch them and then plot the others. Remember that the domain of the regular function becomes the range of the inverse, and the range becomes the domain. Now, either way, you're going to have to change this to exponential because you have no idea how to graph that. Okay, so step 1, we will change to exponential. Actually, let's switch our variables first too, because we're doing the inverse. So make this x equals log base 2 of y. So maybe that's really step 1. So we're going to graph the inverse of it first and then reflect it to get back. Now we'll change this to exponential. So the base stays the base. This would be 2 to the x equals y, or y equals 2 to the x. So that is the inverse of this function. So if we can come up with some values of that, we can then just reflect them across the line y equals x, or we can swap them around. So again, let's pick some values like -3, -2, -1, 0, 1, 2, and 3. Just to get a good idea of what's going on. We probably did this one last week anyways. So 2 to the -3rd will become 1 over 2 to the +3rd, which will equal 1/8. 2 to the -2nd will be 1/4. 2 to the -1st will be 1/2. 2 to the 0 is 1. And then we'll just get 2, 4, and 8. Okay, so make sure you realize that this table is not our final answer, that's the inverse. So to come up with a table for the equation y equals the log base 2 of x, you're just going to switch your values. The y column will become your x column, and vice versa. So we'll have 1/8, -3, 1/4, -2. So we'll swap our x's and y's. And then we'll plot those values. So 1/8, -3. 1/4, -2. 1/2, 1. Uh-oh. -1. No, that's not matching. 1/2, -1. 1, 0. 2, 1. 4, 2. Something like that. Now, if you want to graph the inverse as well, you can, but it didn't ask us to. It just asked us to graph the logarithmic function. So this is the only one you actually need to plot the points. But if you wanted to graph the other one, it would be over here somewhere because it would be reflected about the line y equals x. All right, see if you guys can complete the 2 closures while I pass out your homework, which again is a work.